Hi. Thank you very much. Yeah. Good morning, everyone. I'm Shafi Rahman, and I work for FICO as a principal scientist. And the other gentleman listed over there is my boss, Scott Zoldi, who is the chief analytic officer of the company. You might be aware of our company. We are the company which makes the FICO score that kind of determines at what rate you will get your mortgage and things like that. Okay, so can you hear me?
Now, yes.
Yeah, okay. Let me see if I can. Yeah. And let me check if the clicker works. Yeah, okay. So, yeah, so a little bit of context to help this presentation go forward. I'm going to be talking about self-learning models in the context of how we secure payment card transactions and cyber networks. So back in 1992, we introduced a neural network-based model. This model allowed the banks to significantly reduce the credit card fraud transaction over a very short period of time as adoption increased. Right? So when we were working on this, we gained quite a bit of domain expertise as to what works and what doesn't. Right? One of the things that we learned is that human beings are not static, right? They evolve and hence their behavior evolves. The other aspect that we learned is that the criminals are also not static. They're always experimenting. When it comes to the credit card fraud, they're always innovating new kind of fraud schemes. When it comes to hacking networks, they're never using the old techniques, right? The moment there's a new kind of exploit available, they'll do a zero-day attack and things like that. Right, so signature-based techniques that kind of looks at past behavior pattern works, but it has its own limitation. Right? So okay, I'm getting the hang of this. Yeah, so I think the key aspect that we learned is that we have to have a self-learning capability in our models in conjunction with whatever supervised learning methodology that we are already using, so that the system is continuously monitoring what's going on. It's imbibing all the data that is being emanated from the system that it is being given responsibility to protect, right? And as it's looking at the incoming stream of data, it should be evaluating what kind of shift in behavior pattern is happening. And from that shift in behavior pattern, it should be able to discern whether that shift is a genuine shift or is it a shift which is malicious in intent. Right? So going back to the payment card protection schemes, the model works very well. It is able to secure credit card transactions by having very low false positive and false negative rate. But then the challenge with such a system is that it relies on the transactions of the credit card. So if I use a card which only once in a while, only a very tiny sliver of my behavior pattern gets captured in those transactions, right? So to be able to do behavioral analysis of who I am, it becomes a little bit tricky. So I'm just like looking at through a peephole. I'm not getting the full big picture of who this individual is, right? So what we figured out a while back when smartphones started becoming quite, let's say, popular, and we have kept like figuring out to utilize mobile phones since then, is that people are always using their phones, and if we could figure out a way to harness that information that comes from the behavior pattern on the phone, right? So our analytics, which is deployed today, is deployed inside the apps of the various banks, right? And it's constantly looking at what the person is doing, right? All the data that is coming from the device based on the human behavior, the user, that gets captured, and that informs our analytics. So the rest of the presentation is about how do we do that, right? So, and that information then goes on to kind of augment the existing supervised models that are there in the production to figure out, to decrease the false positive rate as well as false negative rates, right? So the data that we use is basically captured in a very unobtrusive manner by the app that the banks deploy. on our behalf. Okay? And it includes things like what is the device, what kind of OS, and you'll be surprised that even things like what kind of OS you are running or how frequently you update your app or the operating system on your phone has a lot of information power. Right? Location is very, very important in this kind of analytics. And what kind of network you are on, how many times you're hopping the network, and so on and so forth. Right? And what kind of behavior you are doing in the app. So how many times you log in, how many times you are doing transactions, what kind of transactions you are doing, so on and so forth. And last but not the least, all the biometric information that can be captured from the devices. Depending on the kind of device you have, we can capture less or more of the biometrics. But the key thing is that we do it in a way that the user doesn't have any friction. So they do not get asked to, for example, do a two-factor authentication by putting a passcode that is generated or message to them or clicking on an approve or disapprove button. That's not what we are doing. So when we look at the stream of the data that is coming, right, from any device, it's a huge amount of data because as people are moving around, even that is creating a lot of continuous stream of data, right? So it's very, very important to figure out a way to compress this information so that our models can understand that, right? So we use this idea derived from the Kalman filter like techniques where we kind of look at the incoming information and we try to retain a state or previous state of where the person was in terms of their behavior. So this is a signal extraction, or some people call it feature extraction technique. So we are looking at time t a bunch of features that we want to compute, and that is dependent only on the immediate information that has come in and the value that was computed in the previous iteration. So it's an iterative, low time and low space kind of solution. Right? But what happens with this kind of information is that it only tells you that what the individual is doing. Right? So for example, let's say I hop the network very frequently because I keep traveling. It's normal for me. But someone who lives a very sedentary life, maybe 9 to 5 office goer, will not see such a frequent hop in their network. And so what is legitimate behavior for one person is not legitimate behavior for another person. And that can be figured out only if we know how to quantify that who those different people are. Okay? So to be able to do that, what we do is we look at all this stream of data and we represent all the data in some sort of token format. And we can talk about this later during question and answer, but I'll go through this a little bit fast at this point of time. And from that, we try to figure out that what are the different kind of roles that human beings play in their life, right? When I'm using a mobile phone, what are the different kind of what we call archetypes, right? That different individuals belong. And the interesting thing is that different people can wear many persona, right? They can wear many hats, right? So it's a sort of a soft clustering technique, right? It is based on the concepts from Bayesian learning, which derives these archetypes, doesn't presume that what kind of distributions are going to be in the beginning and learns over a period of time. What we do here is that when we kind of process all the data by tokenizing the data, and each of the token essentially is capturing some sort of behavior aspect. So here, for example, one of the tokens says, okay, location change at 9 o'clock in the morning on Tuesday, right? It could be Wednesday, Thursday, Friday. Right? So when we tokenize all the information and then process through this Bayesian learner, we're left with a few dozens of archetypes, which are usually sufficient to represent the customers, all the customers, as you will see in the next couple of slides, right? So what are these archetypes? Like maybe an archetype could be a gamer, other one could be 9 to 5 office goer, as I said earlier. Other one could be graveyard shift worker, like someone who is a nurse or a security guard, right? So their behavior pattern are going to be very, very different, and hence we'll be able to kind of do a better job of understanding what they are doing in the context of who they are, right? The other aspect that we do is that we keep this archetype distribution, so we represent all the customers as a mixture of these archetypes, and then as the customer's behavior evolves, right, we kind of can recompute this mixture or distribution across all the archetypes, right? And something dramatic happens. It's not unlikely for the archetype distribution to start looking very different than what we set out to do in the beginning. Okay, sorry. So this can happen, and this can tell us a lot more about the individual. Okay, so the other aspect of this archetype distribution is that when we kind of look at individuals in the archetype phase space, then we kind of see that they naturally coalesce together into some clusters, right? And that's very interesting. What it says is that not all combination of archetypes is possible, right? So a 9-to-5 office goer and a graveyard shift worker is probably not going to happen together. So you'll not see the same individual having the high probability of both, right? And so there's a lot of kind of gaps in this phase space, and these individuals kind of very nicely cluster into few manageable number of clusters. This we see repeatedly across various domains. So I have another example after this, which I'll run through, but you'll see that this happens across various different kind of business problems, right? So in this situation, what can happen is, so one of the three things can happen. The first thing would be that the customer starts out in a particular cluster and moves around a little bit in that cluster as the behavior pattern evolves, but they remain more or less within the cluster, which means that they are behaving more or less exactly what we would expect them to be, and it's very informative, right? So then we juxtapose this information with what they are doing on the credit card transactions and things like that. We can do a better job of figuring out whether the transaction is genuine or not, right? The other situation that can happen is that the person sets out from one cluster, it starts moving because of the evolving behavior pattern, and just go out. Sorry, I think I'm going faster. Okay, so out of the cluster, and they are now part of none of the known clusters that exist, right? And what this says is something which is that this situation has never been seen in the past, or is very, very unusual, right? Could be that the person's phone has been hacked into or stolen. So it has an application beyond just protecting the credit card transactions. The third scenario is that person moves from one cluster over a period of time into another cluster, which represents that the person has gone through some sort of significant life-defining change. Right? It could be that a party goer suddenly realizes that that person is going to become a parent, right? And that can lead to change in their behavior over a period of time. And we'll see, oh, the person is going. And suddenly all these purchases that they never did, right, on their credit card starts making sense because, oh, well, this person didn't spend $1,000 on a wedding ring or whatever, right, ever. But yeah, it is genuine because this person is not deciding to get married or whatever. So we are able to do this kind of analysis just by looking at how the individual is moving through these clusters, okay? Now the other aspect is I talked about the behavior that we are trying to analyze or quantify using the profiles, right? So what the person does. It becomes much easier to talk about those behavior in the context of who these people are. So now for each of these clusters, I can go back and say, oh, this is the profile or the feature that I had extracted from all the incoming data, and now it makes much more sense because different clusters have different distributions, right? I've just shown one single distribution here, schematic of course, but you can imagine that different clusters will have different distribution for each of these for the same feature, right? Now the other thing that we do is because the data is coming in real time, to be able to kind of say that, okay, this is an outlier, right? We compute various percentile values for each of the feature in real time using an online learning mechanism. Okay. And then eventually we bring all these information together as to what is the value, current value of the individual in the context of the cluster that they belong to, right? So that becomes the peer group, right? And what are the different percentile threshold values that we are interested in. So it could be that SP and SR SL could be same because we just want to kind of say, okay, between 98 and 99 percentile is unusual, right? Or we may want to have like 3 different fulcrum points there to kind of say that, okay, between this and this range they are somewhat unusual, and between this and this range they are much more unusual, right? And we can do that, and then we can bring multiple such features together and do a weighted sum of that to just say that what is the likelihood that this is very, very unusual behavior that we are seeing, right? So the various features Xi's, right? And then the thing about Wi is that we are operating in the domain of unsupervised scenarios, right? So Wi will usually be judgmental, but if you start collecting a little bit of data, right? Then you can start about the responses, whether it was genuine, not genuine transactions, and so on. Then you can start learning these WIs as well. The last thing is that all these features that are there, they are very, very, we are computing like 10,000 features approximately, right? So you cannot just dump all those features into a model, right? So what we do is that we kind of rely on a idea from ensemble techniques, but kind of a little bit of judgmental approach to that instead of throwing, using a kitchen sink approach to that, right? So what we do first is that we do a factor analysis to say, okay, these are the various group of features, right, which are highly correlated to each other. Then second thing that we do is that we create all these self-calibrating outlier models that I showed in the previous slide, but only taking 1 or 0 of the feature from each of the groups, right? So we do that, and then the output of each of those outlier models themselves then get clubbed together to create a single unified score. So you can see that it has a power of ensemble, but it is also judgmentally decided as to how we want to bring these together, right? The last point here is that this kind of, we can learn the weights of how these different outlier models club together to form a single score, right? And this can be, again, like either simple weighting or, or it could be learned over a period of time with data if there's data available. Our continuous challenge in this kind of situation, of course, is that, you will not have a lot of response data in the beginning, so you start with the judgmental, which, banks are pretty comfortable with. The other situation that happens is that you can look at the score and go back very easily and say, okay, what is driving the score, right? I'll give you an example of that. Okay, so till now I went through in detail a single use case. I'll just demonstrate to you in the next 1 or 2 minutes at the max that how the same concept can be applied in a very different scenario of cybersecurity, right? The same concepts of profiling and archetypes and outlier models and multi-layered self-calibrating models, right? So we look at the packets, right? So we have these packet sniffers that we install on our customers' network. They are continuously looking at what kind of packets are emanating from each of the component of the network. And then we unpack that information to say where the information is going, what is the payload, what kind of protocol port, all those things, right? And this allows us to extract those profiles that I talked about in the previous example. So it explains that what these different components in the network are doing. So the next thing that we do is that we kind of process the same data by tokenizing and through that Bayesian learner and extract the archetypes. So we can come up with an example of, oh, these are some of the, one archetype could be our corporate server. The other could be a computational server. The third could be an email server. Fourth could be time server, whatever, right? So you have like all these archetypes. And the interesting thing is that most of the components in the network are a combination, right? Because they serve multiple purposes, okay? Then we pass it through the outlier models, right? And using the clusters of the archetypes as the peer group, we are able to say that whether the behavior that we are seeing is unusual or not, and club them together through a multi-layered self-calibrating model, the ensemble that I talked about. Okay, and it may give a score, right? Which, when it is high, says that someone is actually trying to attack your system in real time, right? So this is one example that we recently saw from a customer. Right, so we got a score of 903, which is not very common. 903 is essentially like we multiply the 0 to 1 score with 1,000, right? So 903 is more palatable than saying 0.903, right? So we get us a very high score, which is pretty unusual in itself, and then we kind of go and see what is going on. And a bunch of things that are happening, right? The archetype was overwhelmingly a corporate server, but what we see is that this server is trying to kind of send tons of data to outside multiple servers, right? And once we saw this, we were able to stop the attack, right? But if we had not in time, then it would have been a big disaster. A lot of data could have been shipped out. So to summarize, right? We use all this transaction data, all the streaming data to quantify the behavior of the individual. Then the same data is used to say who these people are. And then we bring all of them together into calibrating outlier model to say what is the outlier behavior and club multiple such models into a single score, which tells us with a very high degree of probability whether something unusual is happening, which should not happen or not. Thank you very much.
So questions for our speaker? I have a question. I mean, if you guys don't have a question. Anyone? Oh, over here.
Thank you for your lecture. I have a question regarding the encrypted data, where you said that you install the snippets and then you see the packet, right? But what if the encrypted data that puts more load on your stuff, and sometimes if you are decrypting, then typically can we trust that the networks or the infrastructure that company is running, somebody can typically decrypt, right? So how you can envision that as for the, what do you call, data encryption?
Yeah, okay, great question. So when we look at the packet and unpack it, what we are essentially looking at is the header part of it and not the rest of the body, right? The header part remains unencrypted so that the transport of the data can happen, right? So we are looking at what port, emanating port, destination port, what is the destination server, what kind of protocol, and so on. So if we start seeing, let's say we suddenly start seeing a corporate server going out to Amazon AWS, it doesn't have any business doing that, right? Its archetype doesn't justify something like that. Then we know that something unusual is going. But we are not going to rely just on that. We'll be looking at various such dimensions, right? A port that it should not be sending data from, a port that it should not be sending data from. So all those things come together in the profiles that we create, and then the archetypes that we generate, right? And the juxtaposition of that. But you are absolutely correct. We are not looking at the actual payload.
So I think that's it for our questions, given our time constraints. I'd like to again thank our speaker. Yeah. Give him one more applause.
Thank you very much.